Today's lesson is section R1. We will be studying three concepts today. Different types of numbers, those include both real and imaginary numbers, properties of numbers, and order of operations. Now for types of numbers and properties of numbers, there's many names and properties that you're going to have to memorize. And every single year I have many students who just do not take the time to memorize the properties of numbers, and they do not do well on the quiz and test. So please make sure you are memorizing and understanding the types of numbers and properties of numbers. So let's start off today's lesson with types of numbers. So all the numbers that you know right now are pretty much real numbers, I would say. But you can go a step higher than real numbers and classify every single number as a complex number. And a complex number are numbers that include both real numbers as well as imaginary numbers. So for example, the number -5, that's a real number, but you can also classify as complex. Anytime you have a negative number underneath a square root, not a cubed root, not a fifth root, but a square root, and also technically a fourth root, a sixth root. Anytime you have a negative number under a square root like that, that is classified as an imaginary number. And later on you'll learn how to simplify those imaginary numbers. But the way you would simplify them is to, you'll end up using the letter I to denote that it's imaginary, so to say. So for example, -4i is imaginary, and really the I is supposed to be like a cursive like that. 2i, radical 2, that's also imaginary. Now this last number here, 3 plus 2i, the 3 is the real part, and then the 2i, again, the I should be curled a little. The 2i, that's the imaginary part. So a complex number can be purely real, it can be purely imaginary, but it can also have a real part and an imaginary part, like that last number there, 3 plus 2i. 3 is the real part, 2i is the imaginary part. A number like -5, it only has a real part, it doesn't have an imaginary part. Okay, now down from complex numbers, you can then talk about the numbers that you probably are very familiar with, real numbers. Those are pretty much all the numbers you've learned since elementary school through probably junior high. You may not have ever heard of real numbers before today. Again, real numbers, because we haven't learned how to simplify real imaginary numbers yet, just look for whenever it has an I like that, that's denoting that it's imaginary. But if it also is a square root and it has a negative number underneath that square root, that is also an imaginary number. So like the square root of -8, that's imaginary. Again, it has to be a square root or a fourth root. If it's a third root or a fifth root or anything like that, those would not be classified as imaginary. So if you had the fourth root of -8, that would also be imaginary. The third root of -8, that is not imaginary. The square root of just 8, that would not be imaginary. You need a negative number underneath a square root in order for it to be imaginary. Okay, well, that's as involved as you get with imaginary numbers. It's imaginary, and that's all there is to it. However, with real numbers, we can classify them more and more, finer and finer. And so the next step down from real numbers is to classify it either as a rational number or as an irrational number. Now, essentially, a rational number is any number that is that's either a whole number, an integer, or a fraction. So like 1/2, 2/3, 10. 10.5, because 10.5 is really 10 and a half, and you can write that one as 21 halves. So anytime a number can be written as a fraction, now be careful here. Radical 3 over 2, that is technically a fraction, but the fractions that I'm talking about, the numerator and the denominator, have to be integers. Integers are essentially just whole numbers that are positive or negative. So as long as you can translate a decimal or a number into a fraction, a ratio of two integers, then it's classified as a rational number. So radical 3 over 2, because the top and the bottom, the numerator and the denominator, are both not integers, whole numbers, positive and or negative, then it's not a rational number. So radical 3 over 2 is not rational. The definition down here you don't really need to know, but if you're intrigued with higher mathematics, this is how you formally state the definition of a rational number. It says any element where when you choose two numbers, we'll call them P and Q are integers. Of course, the denominator should not equal 0. And you write the ratio of those two numbers as P over Q. That's a rational number. This vertical line right here is a such that sign. So you'd read this as any element of the set P divided by Q such that P and Q are integers and Q does not equal 0. You do not need to know this formal definition at all. Okay, so then irrational numbers are then any numbers that can't be written as a ratio of two integers. So you can't write them as a ratio of two integers. In decimal form, these decimals would not terminate. These decimals would not repeat. Now repeating, I mean they're repeating the same block of numbers every single time. I didn't say that they have a pattern. I said that they're repeating the same block of numbers every time. So if you look at the last number here that I gave you, there is a pattern to that number, but because I can't write it as a ratio of two numbers, I can't classify it as a rational number. So that's why that one is irrational. Now granted, you can follow the pattern and you can continue expanding that decimal form, but again, it wouldn't be classified as a rational number. I can't write that as a ratio of two integers. Pi, if you were to expand out pi, no block of numbers repeats every single time. So pi would be considered irrational. Now, pi, often people use 22 over 7 as an approximation for pi, but 22 over 7 would be classified as rational, whereas pi is irrational, because 22 over 7 is not the exact equivalent of pi. It's an approximation, just like 3.14 is an approximation for pi. 22 over 7 is an approximation for pi. So 22 over 7 is a ratio of two integers. That's rational. Pi can't be written as a ratio of two integers, so that one is irrational. By the way, another irrational number you should become familiar with is e. And we'll talk more about e later on, but you should put e in your memory bank just like you have pi in your memory bank. Pi is approximately 3.14. E is about 2.718. And yes, you should remember that. That will definitely come up quite a bit in this class, particularly chapter 4. And then E will also come back to your senior year when you take calculus. So again, remember that pi is 3.14. E is just a little bit below 3. It's 2.718. Okay, so irrational numbers, that's all we talk about. But rational numbers, we can classify those numbers even finer. And so down from rational numbers, we talk about integers. Integers are essentially whole numbers that are both positive and or negative, including 0. Then down from integers, we can talk about whole numbers. Whole numbers are essentially all the positive numbers of the integer set, and also including 0. And then we can go one step further. Natural numbers. This is probably how you started to learn how to count in kindergarten and probably before kindergarten. So the numbers 1, 2, 3, dot, 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 all the way up to infinity. Those numbers are classified as natural numbers, aka counting numbers. Now, while some of you are catching up on taking down notes, today you're going to have a worksheet that will help you practice the different types of numbers. And at the top of that worksheet, you'll see that there are symbols for each of the different sets of numbers. It's kind of cool if you could remember this stuff, but it really isn't necessary. So for instance, integers, and I don't know why, it's probably the origin of the word integers, but they give the letter Z for integers. Usually what you do is you write kind of like the letter, you write it the letter double. So that's why I wrote a Z and then I wrote a Z offset from it a little bit. For example, the real number set is given the letter R. And so usually you'll write 2 vertical lines and then the R. Whole numbers, I don't think there's a letter for that one. Natural numbers is the letter N. Oh, and back up a sec. For integers, if you want to talk about just the positive integers, which are essentially the natural numbers, then you would put a plus sign above there. If you want to talk about the negative integers, then you would put a superscript of a minus sign or a negative sign to the right of the integers. Okay, so that's one part of today's lesson, types of numbers. The next part of today's lesson are properties of real numbers. And again, you do need to know these properties. You need to memorize their names because what I'll do is I'll give you an expression and I'll say, okay, what property is this? And you need to give me the name of the property off the top of your head. No word bank. We're in high school now. So the first property is called the closure property. And by the way, these properties are only for real numbers. Imaginary numbers have a different set of properties, a different set of rules. Some of them overlap, but okay, first property of real numbers, the closure property. The closure property just simply says that if you were to add 2 real numbers, you're going to get a real number. There's no way for you to add 2 real numbers and get an imaginary number. If you were to multiply 2 real numbers, again, you're going to get a real number. Now that seems kind of intuitive, but when you then start playing around with imaginary numbers, if you were to add 2 imaginary numbers, for the most part, you're still going to get an imaginary number. However, if the 2 imaginary numbers cancel each other, you would get 0, and 0 is a real number. So there's one example how these properties are only for real numbers, not for imaginary numbers. One more example. When you multiply 2 imaginary numbers together, you actually get a real number. So that's why I can't say that these are properties for imaginary numbers as well, because I just gave you 2 examples where the addition and multiplication operations are not closed within that set. Okay, the next property is the commutative property. You probably have heard of this one. This one just simply says that if you were to add 2 numbers, let's say our 2 numbers are A and B, you would get the same answer if you reversed the addition of those 2 numbers. So if you take A plus B, you're going to get the same answer if you added B plus A. Same thing with multiplication. So the commutative property of multiplication says the same idea. If you were to multiply 2 real numbers together and then you reverse the order of the multiplication, you're going to get the same value. The associative property is very similar to the commutative property, except you deal with 3 numbers. So if we were to add A, B, and C, and let's say we add A and B first, and then we added C, well, that's going to be the same thing if we add B and C first and then add A. Same idea with multiplication. If you multiply A and B together and then you multiply C in, you're going to get the same value if you decided to multiply B and C first and then multiply A in. And so that's the associative property of multiplication. Okay, next property is additive identity property. The next few properties are definitely useful when you're solving equations. So the additive identity property says that if you were to take a real number and add 0 to it, you're going to keep that same real number. It's not going to change its value at all. So a real number A plus 0 is still going to give you the real number A. The multiplicative, that's a fun word to say, the multiplicative identity property kind of says the same thing. You have the word identity in this property, so just think that identity, you want to get the same thing back. So you want to deal with multiplication, you want to be able to get the same thing back. So if you take a real number A, what can you multiply to A so that you still get A? Well, 1 would be the number. So multiplicative identity property says that any real number times 1 will give you that same real number. Okay, 3 properties to go. Additive inverse property. Now the inverse properties, you want to get either 0 or 1 as your answer for these. So the additive inverse property, I want to be able to take a real number, add something to it so that I get 0. Well, if I take a real number A and I add its opposite, let's say it's negative A, then I would get my 0. So that's the additive inverse property. And that you use a lot when you're solving equations. If you have a number on the left-hand side and you want to move it to the right-hand side, the way you do that is by adding the opposite of that number to both sides of your equation. The multiplicative inverse property is the same idea. I want to use multiplication. I want to take my real number. I want to multiply it by something so that my answer is 1 then. Well, in this case, I'd want to multiply by the reciprocal of that number. So if I take a real number A and I multiply it by 1 over A, I'll get 1. Okay, and the distributive property says that if you have a real number times the quantity of 2 numbers being added together, I have a choice. I could either just go ahead and add those 2 numbers together and then multiply it by A, or I could use the distributive property, which says that you can multiply that value A into the parenthesis group, multiplying it to each term, and then add those 2 products, and you would get the same answer. So A times the quantity, B plus C, will give you the same value, is equivalent to, rather, A times B plus A times C. So let's see here. 1, 2, 3, 4, 5, 6, 7, 8. You essentially have 8 properties that you need to memorize. Again, I will give you some type of expression. It could either be abstract, like I wrote the properties here for you, or it could be a very specific example, and I'll ask you what is the name of this property being illustrated, and you need to be able to give me the name of it. And for kicks, let's say spelling does count. Okay, so we're 2/3 of the way through our lesson. So the last concept then for today is reviewing order of operations. Now before I show you these examples, order of operations, some of you remember PEMDAS. So the P stands for parentheses. Now I'm going to add in there though that your very first step for order of operations is parentheses or brackets. Then your next step, the E, stands for exponents. Well, since we're in advanced Algebra 2 class, with this line, I'm also going to add in another one. I'm going to add in radicals. So exponents and radicals are in the same playing field. The M and the D in PEMDAS stands for multiplication and division. Now, just because the M is first, that doesn't mean that you get to multiply first before you divide. Remember, you decide this by working left to right. So if the division comes first, you do the division and then you multiply. It doesn't mean multiplication is first and then division is second. Okay, and then the last two letters are addition and subtraction. And the same deal holds here too. Addition is not higher up on the scale than subtraction. They're on the same playing field, and you have to work left to right to decide which one to calculate first. Okay, so we have three examples here. There's example 9. There's example 10. And there's example 11. So I think I would actually like you guys to try these three problems on your own. And I don't want you to use a calculator either, because all three of these problems are very doable without a calculator. And on your quiz and test for this class, these would most definitely be on a no calculator part of the quiz or test. So go ahead, take, I don't know, maybe 3 minutes, solve these three problems, talk to your neighbors, see if you get the same answers, and then we'll go over answers in a little bit. Good luck. One little note here. Please do make sure that you are showing your work neatly and organized. I do try to give you partial credit, but if I cannot follow your work, then you're not going to, it's very simple that you're not going to get partial credit. Now, this isn't to say that you have to show every step of your work, but you have to show enough that I could recreate what you were thinking and I can follow your steps. One little note on problem 11, many students, for some odd reason, I don't know why, always want to try to subtract first rather than multiply. Realize that this 8 is being multiplied to this parenthesis group. So you have a choice here. Do you do the subtraction first or do you calculate the multiplication first? Well, multiplication is higher up on the order of operations, so you should be multiplying first before you subtract. So do not fall into that trap. You should not be subtracting those two numbers at the very beginning. Okay, so those are your three answers. Example 9 is -23. Number 10 is 6/5. And number 11 is 40. Again, with problem 10, leave your answers as improper fractions. There is no need to change it to a mixed number. If you were allowed to use a calculator, there's no need to go to a calculator and change it to a decimal. So learn to leave things as exact answers as simplified fractions. Okay, so we have two examples left. With these two examples, it's also order of operations, except the trick with these is that you're given an original problem. That's the first line. So this is your original problem, and then you have this fraction here as your original problem. And what you need to do is you need to go step by step and figure out the mistakes that this person made. And then based off of their first mistake, see if they made any other mistakes. So, problem 12, you have 3 times 4 squared minus 7 times 5. The next line that someone wrote down was they wrote down that we should now calculate 12 squared minus 35. So from the original problem to the second line of work, did they make a mistake? And what is that mistake? Well, the mistake they made was that they should have calculated this exponential part before they multiplied. You cannot multiply the 3 and the 4 together. So that was their first mistake. This right here is incorrect. Okay, so now to continue with this game, did they make a mistake from this line of work here to that line of work? No, they didn't, because 12 squared is 144, and they kept the 35. So that line of work is fine. So far they just made one mistake. Okay, then did they make a mistake from this last line of work to where they wrote down their answer? Well, is 144 minus 35 109? And it is, so they did not make any mistakes. So the only mistake they made right here was they should not have multiplied the 3 and the 4 together. They should have first calculated the 4 squared and then multiplied 4 squared by 3. Okay, example 13, same idea. So the original problem is 3 to the third power minus 5 times 3 divided by 36 divided by 12. So again, from the original problem to their first line of work, did they make any mistakes? Well, they did two things in this step. They went ahead and they calculated the 3 cubed. So ask yourself, is 3 cubed 27? It is, so that is not a mistake. The other thing they did was they went ahead and they divided the 36 and the 12. So is 36 divided by 12 3? It is, so there are no mistakes in that line of work. Okay, now here is where they jumped quite a bit. So from the second line of their work here to this third line of work, what did they do? And then you have to figure out, is that a mistake? Well, the thing that changed from that second line of work to the third line of work is that they had canceled these 3's here. So the question is, can you just cancel the 3's like that? And the answer is no, you cannot. If you had 3 times 9 minus 5 times 3 divided by 3, this is classified as one term, this is classified as another term. If you were to divide all 3 of these terms, the 2 in the numerator and the denominator, by a common number, then that's valid. But you cannot just pick 2 of these terms, like those 2, and divide them by the same number and leave this guy out. That is not allowed. So that's their mistake. They were not allowed to cancel these 3's here. If they wanted to cancel those 3's, then they would also have to cancel 3 from the 27. And in that case, then they would have gotten 9 minus 4, or 9 minus 5, and then their answer would have been 4. Okay, so the mistake there, they canceled the 3's, but they didn't cancel 3 from everybody. Okay, then the next question is, did they subtract wrong? Is 27 minus 5 really 22? And it is. So again, problem 13, there was only one mistake. Okay, that's it for today's lesson. Good luck with your homework tonight. And again, start studying all those different types of numbers as well as those properties of numbers. I'm telling you straight up, on the quiz and test, you will be responsible for knowing the names of those properties. They will not be given to you. Okay, so have a great day and see you back here tomorrow.